fear that my talk will not be very good because I couldn't sleep very well yesterday night. I could not stop thinking about that video of Porsche. Yes, you know. So if that video is correct, I made a huge mistake 45 years ago when I decided to start to study very hard in order to at least try to answer all the questions of my old teachers at school. So if I had not do that, perhaps I would have a Porsche Carrera today, you know, because that's what was the video. Okay, so my name is Soares de Andrade, and I will talk about complex systems, as Guilherme said very nicely. So I have to make a small introductory part of the talk. I will bother you for 5 minutes, and I have to make a conceptual definition of complex systems. The one I like most is this one. These are systems made of many simple elements that are connected, and these connections can be interactions, in the form of a complex geometry. And the complex geometry comes as a network, usually. Networks like this one, which is the logo of Insight. So I will put this glass here, because I have to talk about chaos. No? So this is the most popular network that physicists like, a regular one. Why? Because it's simple. You have a site and a link. These are the simplest ingredients that you can think in terms of a network. And in this particular case of the network, it has what we call an invariant, or a constant number of connections. Every site has 4 connections. So, but like this one of Insight, which is very similar to the one I plot here, you can have a complex network in the sense that the number of connections of each site can be different. They can follow what we call a statistical distribution. Okay, so this is the very simple definition. And so, as Guilherme said, there is molecular chaos. So how a physicist could enter in a subject like that? So is there any similitude? Is there any analogy between molecular chaos and social physics, for instance? So I would like to draw this attention to you. So the essential ingredients when you talk about molecular chaos is that you have particles, like we have in the air or in a fluid like here, and these particles, they interact with each other. Okay? So despite, I would like to write here, despite the inherent simplicity of the elements, of the ingredients of this system, you can, as well as the form of the interactions between the particles, they can display complex behavior. And this complex behavior can be, for example, shown in terms of phase transitions, when water goes to gas, pattern formation, as you see everywhere, natural pattern formations, or fluid turbulence, when you smoke a cigarette, which is not a good idea. But you see the flare of the cigarette flowing around in a very funny, nice structures and patterns. So the same can be, a very nice analogy can be made between physics and molecular chaos. In the case of the social systems, the essential ingredients are the human beings, us, for instance, and they interact with each other. In this case, it's slightly different because despite of the complexity of the elements and the nature of the interactions, you can see regular behavior that you would not expect. For instance, you might have consensus in terms of opinions, like my talk was very bad or something like that. Everybody might say that at the end. You can have emergence of a common language, which is for me a fantastic phenomenon. The fact that I'm trying to talk to you, something here, trying to make myself understood, and the fact that you might be understanding something, for me it's already a wonderful thing. Okay? So, and also diffusive patterns governing the movement of peoples. People walk in an organized way without you telling them to do that. So there is some sort of collective emergent behavior between people when they interact with each other. So I'd just like to show you a molecular chaos simulation. So you might watch this glass here and think that nothing is going on inside, but there is gas inside of that. And the particles of this gas are interacting like this. And this is a real molecular dynamic simulations made from a computer. And in these molecular dynamic simulations, I used a very simple type of potential to determine the interaction between the particles. They have repulsion. They repel each other when they are very close to each other. And they attract each other when they are very far away. Okay? So you could not see at the beginning the interactions between or the distance, but you can see that behind this disorganized, chaotic, or disordered pattern, you can draw a network. Depending, for instance, on the distance between these particles, if you put a line between them, you can see a complex network like that one. So the same thing could be made for the social interactions. You can see people moving and talking to each other, making connections and things like that. So I like to quote Gilberto Gil. It's always good to remember that in an empty glass, there is air. So this is molecular chaos. It's here. You don't see it, but it's there. So now I will bother you a little bit with mathematics. That's the maximum thing you will see from me today in terms of mathematics. I would like to talk about allometry. It's a very simple lesson. So if you don't remember, of course, most of you, there are a lot of physicists here. This is very simple. So what I want to say is the following. Allometry is when you try to relate a quantity, Q, with the volume of that quantity. And you have a relationship like that. Q is equal to A constant A, times the volume to a power alpha. And this volume is very large, let's suppose like that. So you have three types of behavior. When alpha is equal to 1, alpha, the exponent, is equal to 1, you have proportionality. So if you double the volume of that particular measure, you will see that the quantity related with that volume will also double. If it's alpha equal to 1, when you double that, you have more than double. And if it's smaller than 1, that exponent, when you double that, it's smaller than double. So it's a way to measure the proportionality between things. And the simple way that nature shows us something is when it's what I call isometric behavior, when alpha is equal to 1. We are used to that, and we see that everywhere. It's less common to see superlinear and sublinear behavior. So I will also show you a trick, because when you transform, you use this logarithmic thing. When you transform that formula that I showed you before, and you apply the logarithm on the left and on the right, that relation which had a power disappears and becomes a linear relationship. So everything can be put in a log-log plot, and all you will see is that linear behavior, when the log is applied, the linear way will behave exactly as it was before, and the sublinear will be slightly down with a smaller slope, and the superlinear will be slightly up with a larger slope. That's all I need from mathematics for all this seminar, okay? So I hope you remember everything I will show. So now we start with allometry, because I want to go to cities. So I would like to anticipate my target here. And then there is this guy called Kleiber in 1932. He came with this fantastic law. He realized, he was an agricultural chemist, and he realized that if you put in a log-log plot the total metabolic rate of animals, in the case mammals, and their mass, you will see that a whale weighs approximately 10 times more than a mouse, but however, it needs only 3,160 more energy to survive. So large animals live more effectively. So that's what he observed. So it was amazing because he saw all these animals there, and he could group them in a single allometric curve. And of course, there is economy of scale. So small may be beautiful, but it's more efficient to be big. In Brazil, if I say a sentence like that, people will have second thoughts. But in Portugal, I hope it's not like, as you laugh, no, but, so the law is this one, and the exponent is 3/4. So it's not proportional, okay? It's not proportional. That's what Kleiber saw. And why was that? So Kleiber realized that this is why this happens, because all those mammals, those animals, they have in their body structure networks which controls everything in terms of metabolic rates. So the lung network is the first one, and the vascular network is the other one. So networks are there, and this has been explained conceptually by the group of West in 1997 in terms of this structural topology inside of the mammal behavior. Now we go to cities, and we see that this was viewed before, anticipated, by a journalist and also urbanist called Jane Jacobs. And he wrote a very important book in urbanism, The Death and Life of Great American Cities. And she said something about chaos. She said, intricate minglings of different uses in cities are not a form of chaos, if you might think. On the contrary, they represent a complex and highly developed form of order. In some way, she anticipated, she previewed that cities also have some sort of organism. They behave as ecosystems. So perhaps there is some allometric law which governs cities as well. And this was effectively observed by Geoffrey West, the same group that proposed networks to explain the allometric rule observed by Kleiber in 1932. So Geoffrey West showed that there is synergy of a city, in the sense that, for instance, if the bigger the city is, it pulses more. He used this nice verb. So to be more precise, for instance, a city that is 10 times larger than another in terms of population is 17 times more creative in terms of generation of patents, for instance. So, and this was what we call the superlinearity of cities. Unfortunately, this law also applies for the distribution of income, for crimes, for pollution, and as well as for population itself. So these are deleterious qualities of cities in this particular way, which is the opposite for the case of creativity or innovation. So cities can also behave sublinearly. For instance, there is economy of scale, like in the case of the mammals. A city larger than another, for instance, needs less infrastructure per capita. This is what was observed by West. Okay, and okay, so going back, this sublinearity was also observed for different things. So what he said is the infrastructure of a city is like the mammals. For instance, the number of pavimented roads, the electricity supply, the gas stations, the number and the public transportation and cultural devices, they are also behaving sublinearly. So if you double the size of a city, you don't need the double of equipment of culture, you don't need the double of gas stations and things like that. So he observed that and made very nice plots, which are very, very similar to the plots made for mammals. Okay, so we did some work on that in 2014, just to try to understand this behavior. And what we saw, these are for Brazilian cities. We had this big data, and we tried to understand the crimes, the fatal car accidents, and suicides. And what we saw was that when you see the number of homicides for different cities in Brazil, if you double the population of the city, the number of homicides is more than double. It's 24% more than double. So, larger cities are more dangerous. Statistically speaking, of course, we cannot say that punctually. So different things for the traffic accidents, because there is no social network involved. I think killing a person using your car is not a very good idea. So, so the traffic car accidents are isometric in the sense that if you double the number of people in the city, most likely you have the number of car accidents in a fatal way. But what we saw, that was the original part of our work, was that the suicides, they are sublinear. So as more complex or intricate is the complex network which is evolving in the city, you have less chance to have suicides. And we thought that was a fantastic and new idea, but fortunately or unfortunately, this was already more or less devised, envisaged by Emil Durkheim, with one of the pillars of the social sciences today. And he had a very nice book called Suicide. He published that in 1987. And he said that in spite of the pathological things that are involved in this tragic accident, which is a suicide, it might be related with sociology. So the suicide can be related as a social fact. And he did nice studies about that. So this was somehow corroborated recently by a very nice study by this guy and his group, Nicholas Christakis. And he, using the very nice big data from Framingham Heart Study, it's an enormous amount of information from a city in US, and they could draw what they call the network of happiness, in the sense that they were constantly asking people if they were happy or not, and if their friends were happy or not, because this was already mapped in the structure. So he could draw these two networks, and he could come to very, very, very interesting type of observations. The first one is that people who are surrounded by many happy people and those who are central in the network, they're hubs in their network, they are more likely to become happy in the future. So this is very interesting. So the happiness works as an epidemic, opposite to the sadness. So this is explicitly stated in his work. He went further away. He said, a friend who lives with a mile and who becomes happy, because this is a dynamical problem, you are becoming happy and sad every day, he has his probability to become happy increased by 25%. So this is a number. So he could quantify, in fact, he could also quantify the probability that someone can be happy at the next examination in that cohort, in that particular statistics, according to the number of friends who were happy at that particular time. So he could see that this was a monatomic function. As you increase the number of people who are happy surrounding you, you have a greater chance to become happy in the next examination of your doctor. So now we come to a very, very difficult point here, which is the definition of a city itself. So the definition of a city itself, let's take the example of a USA. So there, they have the following definition. They call it metropolitan statistical area. It's quite sophisticated, I would say. So this is defined, according to the US Census of Bureau, as a geographic entity defined by a set of counties which are socio-economically related and with population larger than 50,000 inhabitants. So these are, as I can say about that, this is a standard definition, which is merely administrative. So they define cities as we usually define according to a political administrative boundary. So there is nothing apart from that which defines a city. So we, in 2008, together with Hernan Maxi, these Argentinians, so Brazilians can be friends with Argentinians, not in the World Cup, so we don't talk to each other in the World Cup. So what we did, we tried to define the city in terms of a population map. Okay, so we had this very, very precise population map made from this project, the urban mapping project, the GRAMP V1, in which you have the population, according to this barcode, draw for 1 kilometer by 1 kilometer of a scale. This is a very amplified scale, but in fact you have a mesh size of approximately 1 by 1 kilometer in the sense. So from this mesh you can take a single cell, for instance, and try to analyze that. And then we proposed an algorithm. So we call the city clustering algorithm. And what we do is we take, suppose that this is one of the cells of the United States, for instance. And what do you do now? You binarize that. So what do? You simply know the population of each cell. And if this population is larger than a given value, dy, for instance, you say that it's equal to 1. If not, it is equal to 0. When you do things like that, you generate a mesh like this. So everything which is smaller than that threshold becomes 0. Everything else becomes 1. So you binarize. This is the first step of the city clustering algorithm. And then you create what we call a CCA city. So very different. So it's not the perfect way to define a city, but at least it's a little bit more, less arbitrary than the MSA. So the CCA has some parameterization involved. Okay, so we did that. So now we decided to apply that for a very important thing, which is the emission of CO2. And we published that recently. So we took another very precise map from the statistical generation data science in US and of the CO2 emissions for a slightly larger grid than the population itself. And we apply the MSA and the CCA to that. So we apply the MSA. So we simply made an intersection between this map and the MSA. And we generated this plot. So these are the emissions of the cities according to the MSA way of definition. We also did that for the CCA. So the intersection with the CCA generates this plot. As you can see, this is a little bit more homogeneous than the previous one. And then now we went to allometry. So does it make any difference to do this? The definition of a city can change the definition of the carbon emission for different cities in different definitions. Okay, so what we saw is changes dramatically. So depending on the way you define a city, you might say that cities have a larger or a smaller emission, statistically speaking, of course. So what we see is that for MSA emission case, you see that you obtain something which is more close to isometric than you could expect. So a large city, a city with the double of a population of another one, will probably, statistically speaking, have a larger amount of CO2 emission as a factor of 2, which is not the case for the CCA. When you define the city in a different way, you see that you see a super linear behavior, in the sense that if you double the size of the city will probably have more than double of CO2 emission. So this is interesting. We use exactly the same allometric form for the CO2 in the relation with the population. We find isometric for MSA, superlinear for CCA, And the conclusion is that large cities are less green, contrary to what people thought when you define the city according to the MSA, to the standard administrative definition. Okay, now, oh, this is a bug of my computer, you know. It has been with me since 2014, and I could never erase that. This is a disaster. No? Okay, let's talk about Brazil. No, so we don't even the case is so big that we don't even have soccer anymore. No? So how the Brazilian congressmen vote? So this is a very, very special type of network that I would like to spend my last 5 minutes on that. So this is a work we did together with these two guys here, Carlos Dens and Ludwig Marinho. It's very common in Brazil to acknowledge all your, in physics, all your collaborators. And what we did, we analyzed 513 federal deputies of the higher camera in Brazil, and they voted for 1,355 projects during this period. So I would like to try to explain you what we did here. So what we do, we quantify the votes. There is a way to quantify that, and we want to generate correlations between these deputies to see if they think similarly or not. So for instance, take deputy A and deputy B. And these are the ways they vote. And then, of course, before that, we have to transform their votes in numbers. If they vote no, it's -3, for instance. This is arbitrary, and we will not change in anything our conclusions of this results. And if they vote yes, it's 2. Everything is in the middle, has been more or less quantified in a, I would say, reasonable way. Okay? So, but basically, if they say no, it's contrary to each other, to the project. If they say yes, it's in favor of the project. So A and B voted like that for instance, 40 projects. I put a smaller number than the number I said before, just to show you. So as you can see, they vote in a very similar way. So what do you do that with these two series, like let's call it time series? What do? You correlate them according to a covariance value, which is a number that you calculate in statistics, and see and show how similar a time series is related to each other. So you do this for A and B, they correlate very highly, so it's a high number in the color code here. You do the same for A and C, and you see that they're similar too, so they correlate positively. And there is a transitive process that says more or less it's very likely that A and B correlate positively, and A and C correlate positively. There is a very high chance for B and C also to correlate positively. And this is effectively what we saw. So this is the first group. You do the same for the second group. They vote in a very different way, okay? But between them, among them, they vote similarly. So that's what happens here. You made a connection. You made another one. You make another one. So this is two groups of deputies that they vote in a different way, but they vote strongly correlated and positively correlated. But of course, now if they vote in a way and this vote in another way, they might have an anti-correlation way of voting. And this is exactly what you see when you put B and A. So statistically speaking, when B votes positively, A tends to vote negatively. So perhaps they belong to different parties. Okay? And then you keep doing like that, and you end up with a complete graph of correlations that now you can assign in terms of interactions between these. So they don't have necessarily to interact. Of course they do, and we know that. And this is what you get at the end. So if you go to the entire cluster, that's what you see. You see two groups of deputies vote in a way, and they vote differently, and there are poor or negative correlation between them. So this is the analysis of correlations for the first year of the second mandate of Lula. So what do you see here is that there are two groups of deputies. This is a distribution of correlations, the number of correlations that you have. So if they correlate positively, they are in the same group. They are in the same group. If they correlate negatively, they are in different groups. But now you see that you have something what we call negative correlations, which of course explains you that there is a difference, there is a distance between two or more groups in the system. So that's what you do. My time is almost finished, and I have to go very fast. You can use more sophisticated techniques to prove that there are more than two groups in the system, but they somehow can be close together. In this case, we use the minimum spanning tree, and then that's what we did. So I repeat the same graph of Lula in 2007. So there were differences in the parties. This is the beginning of the mandate. They were ideologically separated, and they were more or less following their voters in their projects. Now what happens in the second year? So for some reason, the number of negative correlations starts to disappear. This is what happened, 2009. And 2010 is amazing, you know, so they all now vote everything in the same way. So the mandate, the first mandate, the second mandate of Lula finished here, and the deputies were in a consensus, no? So evolution to consensus, okay. So now let's go to the first mandate of Dilma. As you see, it already started in a very different way from the first one. So after the first mandate, so they go to the streets, they have to convince their voters, and what they do, they start like that. But as you can see in 2012, already there were more or less consensus in the camera, in the Congress. And it was like that till 2014. So for some reason, they evolved to consensus very quickly. And this is the second mandate of Dilma, the first year when the impeachment took place. So somehow we could predict before that something bad was going on if there were no division in the parties inside of the Congress. So this was our way to analyze that. We're trying to publish that. It's not so easy. I would like to thank you very much for your attention. I leave you with the greatest poet, in my opinion, of the world in Portuguese, which is Fernando Pessoa, talking about science. Thank you very much.